Chancellor, His Excellency Dr. Thabo Mbeki, the Vice Chancellor and Principal of UNISA, Professor Puleng Linkabula, the professor that we are inaugurating this afternoon, Professor Melusi Khumalo, his family members, friends, and loved ones, members of the College of Science, Engineering, and Technology, the management and staff of the college, the executive dean, the College of CSET, its admin staff, colleagues, supporters, distinguished guests, funders, UNISA alumni, boys and girls, and most importantly, to you, Prof. Khumalo, again, a celebrity of the day, Sanbonani, Molweni, Dumelang, Avuan, good afternoon, Goeienaand. I acknowledge all protocol. My name is Professor Tenjiwe Meyiwa. I'm the Vice Principal responsible for research, postgraduate studies, innovation, and commercialization. Ladies and gentlemen, colleagues, greetings and welcome to this inaugural lecture, Professor Khumalo's lecture. He is affiliated with the College of Science, Engineering, and Technology as the head of Mathematics Department. Please allow me again to acknowledge his mentor, Professor Mamba. We also welcome Professor Motsa, the Executive Dean in the Faculty of Science and Engineering at the University of Eswatini, the old Swaziland. He serves as a respondent this evening during this installation. We thank you, Prof. Motsa, for heeding our call. Appreciate it. Ladies and gentlemen, boys and girls, as I know we're all at home, most of us, we will be as we enjoy this inaugural lecture. In these turbulent, challenging times, globally, within the country, and indeed within our sector, our role and relevance as a university is very significant. It actually has to be significant not just only for us as a university, the University of the Land. We are the only university that's named after the country, University of South Africa, but this contribution of this lecture, of its focus on humanity, a university that shapes futures as we call ourselves, is at Adaje, hence the importance of the content of the inaugural address we are due to listen to this evening. It's a lecture that's finding solutions, solutions that are based on science, based on research, and based on well-backed up proven theories. As an institution, while we are bound to produce graduates and research of eminence and excellence, we are also committed and must produce, alongside that, colleagues of the caliber of Professor Khumalo, so that we're able to right the wrongs of society, we're able to deal with societal injustice, and so we're able to respond to not only the African Union's 2063 call, but also the National Development Plan of the country, South Africa, in terms of the contribution we should be making to education that brings about solutions. Therefore, alongside that, is the responsibility of the University of South Africa to produce graduates. And we can't produce graduates, postgraduate students, a good cadre of that without alongside the cadre of professorate of Prof. Khumalo's kind. It is for that reason that we, as the institution, we take such occasions, and this occasion this evening, a very important occasion that we reflect as an occasion that demonstrates the pinnacle of the academic achievement of a professorate. There's nothing beyond being a full professor. Prof. Khumalo, Melusi Khumalo, becomes a full professor post this inaugural installation we're having this afternoon, evening, as you just walk into the evening. Now, you may be asking, what's a full professor? A full professor at a university is somebody who mentors, produces research, produces postgraduate students, good research for that matter, not just research, and ensures that there's networking, collaborations with other universities, industry, as well as raise funds. When you've fulfilled all that I've listed, we then look at your work and say, are you fit to be a professor? And in this instance, that's what we did with Professor Khumalo, Melusi Khumalo. And I'm therefore inviting you that in the chat box on the right-hand side of the screen, please write up comments of congratulations, words of what you may want him to do, because by being a full professor, it's not the end. It's not destination. We still expect more of you, Professor Khumalo. Professor Khumalo's lecture, in terms of the proceedings of this evening, shall be introduced by his mentor, Professor Begi Mamba, the Executive Dean of the college to which he affiliates. He shall provide a brief on him and all that is expected as we had planned. So ladies and gentlemen, boys and girls, family, UNISA alumni, supporters, this evening, therefore, what's going to happen after I've just stepped off the stage is to ask Professor Mamba to come onto the podium, and he will present to us the professorial lecture presenter, that is Melusi Khumalo, and following that will be the respondent who's kindly agreed to do this response, that is Professor Moza, who is from the University of Eswatini, as I made mention of earlier on. I will not be coming in between them. At this juncture, I now invite Professor Mamba to come onto the stage. Professor Mamba.
Vice Chancellor, who is the Vice Principal for Research and Innovation and Commercialization, Professor Thenjiwe Meyiwa, who is presiding over this inaugural address, I welcome you. I also like to welcome the respondent to this inaugural address, who is Professor Sandile Motsa from the University of Eswatini, who has made himself available to be part and parcel of this auspicious occasion. I'd also like to welcome the College of Science, Engineering and Technology, CSET, the management, the executive, academic staff, non-academic staff. And I'd also like to welcome friends and relatives, collaborators of Professor Khumalo. And I'd also like to welcome his family, his wife, Zanele, and his children who are listening and following these proceedings today. And I'd also like to welcome the relatives of Professor Khumalo and everybody who has supported him such that he has reached this pinnacle of his academic career. Ladies and gentlemen, you are all welcome, all protocol observed. And before we invite Professor Khumalo to give his inaugural address, it is my pleasure to read his citation and his brief CV so that you'll all know the kind of person who will be addressing you today. Professor Khumalo's fields of specialization covers computational methods and numerical analysis, with extensive applications in dynamical systems, fluid flow, and fractional calculus. Professor Khumalo obtained his BSc degree where he majored in mathematics and physics at the University of Eswatini. At that time, it was referred to as the University of Swaziland. He then obtained his master's degree in numerical analysis from Brunel University in London, and further on pursued his PhD studies at the Memorial University of Newfoundland in Canada. Professor Khumalo has over 20 years of post-PhD university teaching experience at various universities, which include the University of Eswatini, University of KwaZulu-Natal, University of Johannesburg, and now he is at the University of South Africa, where he is the chair of the Department of Mathematical Sciences. His teaching experience is in all areas of undergraduate mathematics, and his postgraduate teaching has involved various modules such as ordinary differential equations, partial differential equations, numerical analysis, and optimization. As I've mentioned, that he is the current head of the Department of Mathematical Sciences. Before then, he has been the deputy head of department at the University of Johannesburg. And for a number of years, he was the head of department at the University of Swaziland. And as you can therefore attest that his leadership has been tried and tested in a number of institutions. Professor Khumalo is an established scholar and is a C3 rated scholar, meaning that he's an established researcher. And he has published and co-published over 32 accredited publications in reputable journals, and he has written a book chapter. Professor Khumalo has undertaken various research activities in a number of institutions where he has served as a visiting research scholar or a visiting fellow. Amongst those include the Abdus Salam International Center for Theoretical Physics in Trieste, Italy, and has also been a visiting professor at his alma mater, the Memorial University of Newfoundland in Canada, and also the Southern Western University of Finance and Economics in China, the Beijing Computational Science Research Center, the Hong Kong Baptist University, where he went there on a research visit. And recently he also visited the Harbin Institute of Technology, which is a highly ranked institution in China. Professor Khumalo has supervised a number of students and is currently supervising master's and PhD students, of which 8 of the master's students have obtained their master's degrees and 3 PhD students thus far have graduated under his supervision. And he has featured prominently in a number of international and local conferences where he has presented his research in these meetings of high esteem, and has participated as well as a member of the South African Mathematical Society, SAMS, the Canadian Applied and Industrial Mathematics Society, where he's also a member, and also the Society for Industrial and Applied Mathematics, where his membership is quite prominent. Ladies and gentlemen, I would like to congratulate Professor Khumalo for obtaining his promotion to be recognized as a professor at the University of South Africa. And therefore, I would like to invite all of you to sit and listen and watch the inaugural address of Professor Khumalo. Thank you very much.
Good evening, ladies and gentlemen. I would like to welcome you to this inaugural lecture. I would like to first acknowledge the presence of Professor Thenjiwe Meyiwa, who is the Vice Principal research, postgraduate studies, and innovation and commercialization. I would also like to acknowledge the presence of our Executive Dean, Professor Peggy Mamba, who is our Executive Dean in the College of Science, Engineering and Technology. I would also like to acknowledge my dear friend, Professor Sandile Mota, who is the Executive Dean of the Faculty of Science and Engineering at the University of Eswatini. I would also like to welcome distinguished members of the university community, colleagues, friends, family members that are watching this evening. The inaugural lecture will be entitled Computational Methods with Applications to Mathematical Models. Most of life is made up of basically phenomena that are called natural phenomena, which occur in real life. This could be physical phenomena, it could be engineering phenomena, it could be medical phenomena, which take place like the flow of blood in arteries, or it could be the flow of fluids in pipes. These are natural phenomena that occur all around us. Now, mathematicians would like to understand these phenomena by designing and constructing mathematical models. The reason for that is that mathematics provides for us a language through which we can understand certain phenomena that we would not be able to understand otherwise. So mathematicians construct mathematical models, and then we would like to understand the natural phenomena from the mathematical models. In order to do that, we need to solve these models. To solve them normally is very, very difficult because natural phenomena normally are represented by models that are highly nonlinear and highly difficult to solve exactly. Therefore, we normally design computational methods that are able to solve these models in an approximation manner. In other words, we are finding approximate solutions. Once we have the numerical solutions, then we interpret the solutions so that we get to understand what is happening in the natural environment. Now, if we were to try and solve the models using exact methods, the problem is that we would end up with models that we would have to simplify in such a way that the solutions that we obtain would have nothing to do with actually the natural phenomena. In other words, there will be oversimplification of the models. Now, the models that we deal with in our work are represented by functional equations. Functional equations in general, just to simplify, represent differential equations. They could be integral equations. They could be a combination of differential and integral equations, which we call integral differential equations. Now, let's represent a typical functional equation by the equation that is given there, Fu is equal to G, which would be your model. U is your solution. F is some kind of operator. It could be an integral operator. It could be an integral differential operator. It could be a combination, an integral operator of some sort. So that is a simplified version of what a functional equation would look like. So we assume that this functional equation resides in a Hilbert space X. A Hilbert space basically means that it's a set of elements, and these elements we define an inner product in this set which maps two elements in the set. So it results in a Hilbert space X. Then the well-posedness means essentially we are interrogating the questions of existence, uniqueness, and smoothness of the solution, and we investigate this. We establish conditions under which this happens, because if there is no solution, then there is no need to look for a solution. It is essential that this solution is unique within this set, because if there are multiple solutions, then we have a problem. Which solutions are we looking for? So, existence, uniqueness, and smoothness of the solution is our question of well-posedness. We normally prove theorems on that to start with. So we then talk about the computational approach. A computational approach means that we are not dealing with exact methods, because exact methods have their limitations. Computational methods have their limitations as well, but they are approximations that are approximations to the real problem. So the science of seeking more accurate and efficient numerical methods is what is the broad area of what we call numerical analysis. So then we go back to our functional equation. Fu is equal to G. U is in a Hilbert space with an inner product. We assume that the solution is well posed. So let S be, because we are seeking an approximation, then we find a subspace of the X, the space X, of the Hilbert space X, and this is going to be called an approximation space. So, in grammatic form, this is what we are looking at. X is our big set. In general, it could be a set of continuous functions in a closed and bounded interval. And then S is an approximation space. In other words, this is where we are looking for our approximation. An example of that would be the space of polynomials of degree n or less. Now, the problem then is to find a U, big U, contained in S that best approximates this small u, the exact solution, in some sense. Well, in what sense is that? So in the Hilbert space, of course, normally we would want to minimize the residual, which would be that equation there, Fu minus G, which would be our residual function. So then we take because the set S is a part of the Hilbert space, then it is spanned by certain elements that we call phi I. Because it is an n plus 1 dimensional space, there will be n plus 1 elements that will be a basis for S. So we seek an approximation of U such that this approximation is in S. Now, the residual is minimized using the method of weighted residuals. Weighted residuals just means that when we take the inner product of the residuals with certain functions, n plus 1 functions in the space, we get 0. In other words, we want the residual to be orthogonal to a certain test functions in the space. This is the equation there. There are two approaches of doing that. You'll remember that we're talking about basically the choice of the basis functions. How do we choose the basis functions? That's number one. The second one, how do we choose the test functions? Number three, how do we find the best approximation? In other words, that is the weighted residual method. So with Dlamini in 2019, we wrote a paper which dealt with the integral equations, and we used the Galerkin approach. The Galerkin approach essentially means that the test functions are the same as the basis functions. So we choose that one by one, the test functions will be the same as the basis functions. And then if we return to the functional equation, this is what we're imposing. We're imposing that the residual and the test functions form an inner product which is equal to 0, the test functions being the same as the basis functions. Then this, if we assume that the f is linear, then we obtain a system of equations given there, the system of equations that we need to solve to obtain the coefficients phi alpha j, and these coefficients are going to uniquely determine our approximation u. Now the applications that we looked at for the Galerkin, in fact for the Volterra integral equations that we looked at, they are applied in population dynamics, the spread of epidemics. We remember that we are just through an epidemic, and these integral equations can be used to model the spread of epidemics in population dynamics. Semiconductor devices and wave propagation in physics, these integral equations can be used to model these systems. Superfluidity and traveling wave analysis, also from physics, these problems can be modeled by using these integral equations. So we can see then that these are just not problems that arise from the minds of some people, but they come from real life problems which can be modeled by these systems, and then they can be solved numerically or computationally. The second approach is the method of collocation, which is normally called pseudospectral, the pseudospectral approach. This is where the test functions now are not the same as the basis functions, but they are delta functions at specific points. Now these points are chosen strategically such that the system, because of the property of the delta functions, we expect that the functional equation will be satisfied by this method at those specific points. These are called collocation points. In this discussion, we call them xi. Now, using the collocation points, we again construct the approximation equation, and it gives us this equation there in the red box for the linear version of f. Now, the advantage of spectral collocation methods is that they use infinitely differentiable functions as basis functions. The global methods with an exponential rate of convergence, they are global in their nature, and they have an exponential rate of convergence for problems with smooth solutions. So, if we look at an example of what the spectral collocation methods look like, and our special guest here has done an extensive amount of work, Professor Motsa, an extensive amount of work on spectral collocation methods of various types. The basis functions would be Chebyshev polynomials or other orthogonal polynomials, and the collocation points are chosen in such a way that they are basically the roots of orthogonal polynomials of degree n, and these would be given by that. So, if we look at the traditional methods versus the spectral collocation methods, we found that the spectral collocation methods are more accurate, they are easier to implement, and they are effective in solving differential equations defined over smaller domains, particularly over time. The accuracy of spectral collocation methods comes from the fact that the choice of collocation points is given by the roots of an orthogonal polynomial. The disadvantages are that they lead to algorithms that are they give rise to algorithms with dense matrix of equations. A dense matrix basically means that most elements in the matrix are non-zero. That leads to computational difficulties because of the round-off errors that can creep in when you are dealing with a dense matrix, of a dense system of equations. The accuracy of spectral collocation methods should increase with an increase in grid points. So basically, they rely on having more grid points in order to improve accuracy. But then, if you increase grid points, then it means you are doing more computations, which means that you also might be subject to more round of errors creeping in. The way to overcome this, we and other colleagues that have interrogated this problem have looked at the domain and said that if we can use multiple intervals, in other words, we use multi-domain approaches, then it is possible to have an effective methods for both smaller and larger domains. They yield sufficiently accurate and stable results, multiple intervals, they yield sufficiently accurate and stable results which are attained using minimal number of grid points. So we minimize the propagation of round-off errors causing instabilities, and we also are efficient in terms of computational time because of the small-sized matrices that we take at a time. Now, the future of what we are doing right now is to extend the approach of multi-intervals to four-dimensional problems. The single domain can be ineffective here because of the difficulty with four variables. If we are dealing with a four-dimensional problem, then if you are using a single domain, you get into trouble because then there will be inefficiencies that creep in. The second approach that we look at in the future is applying the approach to fractional differential equations, which we have already started, by the way. And then the third approach is to modify the approach to accommodate differential equations with periodic boundary conditions. Not Dirichlet, not Neumann, not mixed, but periodic boundary conditions. The other piece of work that we have done is on iterative function systems. We know that in matrix spaces particularly, we can define a matrix space as a space, like we have defined a binary space, a normed linear space. A matrix space is a set of elements where we have a matrix defined. A matrix can be defined basically in general as a generalization of distance. Elements are related by distance in the set. So an iterated function system is a method of constructing fractals. We talked about modeling before. If we are to look at life, we can see that life contains a lot of fractals. The brain is an example of a fractal. There are several other examples of fractals, and to understand them, we use iterated function systems. Now, the generalized iterated function system is a finite set of generalized contraction mappings. We define a contraction map in the same way that Banach did on a more general complete matrix space, like a partial matrix, semi-matrix, generalized matrix, etc. So this is more general than a contraction mapping, and its advantage is that if we use them to construct fractals, then we are able to understand more variety of fractals. So what we've done is we have obtained the results on partial matrix spaces. We've obtained the results on semi-matrix spaces, generalized G-matrix spaces, and B-matrix spaces. And we can construct those fractals which we cannot obtain in simple matrix spaces. And that is basically a summary of what our work has involved over the years. Finally, I would like to just mention a few colleagues and friends that have contributed over the years to the work that we have done. The first one is our respondent today, Professor Motsa, who is the Dean of Science and Engineering at the University of Eswatini. Professor Tsanwen Yang, who is at the Harbin Institute of Technology in China and has graciously invited me to that institution to speak and to collaborate with him there. Professor Herman Brunner, who is my personal mentor at postgraduate and who is now based at the Hong Kong Baptist University and also has graciously invited me a couple of times over the last few years to visit his institution. Professor Ronald Haynes, who is at Memorial University of Newfoundland, which is my university, and has also graciously extended an invitation for me to visit him and to work with him on certain projects. Professor Precious Sibanda, who is at the University of KwaZulu-Natal, an eminent scholar and a very good friend of ours and a well-known mathematician, also acknowledged with the work that we have done together with him. Professor Chamola there is a misprint there, JP Institute of Information Technology in India, in Delhi, and he's also invited me as a speaker at one of their conferences a number of times, actually, 2 or 3 times in the past couple of years. And then Professor Reza Izzati, who is at the Islamic Azad University in Iran, is also a collaborator of mine. And I would like to thank you for listening and thank you for enjoying this inaugural talk. Thank you.
The Vice Principal for Research, Postgraduate Studies, Innovation and Commercialization, Professor T. Meiwa, the Executive Dean of the College of Science, Engineering and Technology, Professor B. Mamba, the inaugurant, Professor Melusi Khumalo, members of the university community, good afternoon. Thank you for giving me this opportunity to give a comment on Professor Khumalo's research. My brief comments will be centered around the nature of the research and the contribution that Professor Khumalo has made in his area of research and the impact that his research has contributed to science. I'll start with highlighting the nature of the research, which can be described as, centered around basically describing, analyzing, and then solving problems that model real-life phenomena. In most cases, these problems are presented as what we call mathematical models, which are just equations, which come in many forms. Some are called ordinary, partial, integral, algebraic, and many others. But in the limited time that I've been afforded, I would like to, for the purpose of this presentation, zero in on ordinary type of differential equations, which have practical implications that even a layman can identify with. Specifically, I would like to talk about time-dependent initial value problems, in which Professor Khumalo and his collaborators have made significant contribution to the body of literature in this field. A typical model of an initial value problem that models real-life phenomena. In most cases, typically such models would be very complex and they will involve many variables that interact with each other in complex and non-linear ways. I'll give an example of, a model that tracks the spread or how COVID-19 spreads in a community or a population over time. So in modeling this problem, you'd have many variables, which as an example could be the infected population, vaccinated population, those that are not vaccinated, those that have been infected and vaccinated, those that have comorbidities and so forth. So in your model, all these different groups will be interacting with each other because they are contributing to the number of cases, the number of deaths or due to COVID-19. So the model will be very non-linear and will be large because every model has got to capture all the factors that are contributing to the phenomena that you are trying to model. So after capturing this interaction of the groups as an initial value problem, you find that the equations to solve is very complex. So what Professor Khumalo and his group have contributed, in this type of research would be to introduce innovative ways of simplifying such models, specifically through linearizing the models and also introducing methods of solving the problems in multiple domains where the interval where you're expected to solve, that is the time interval, is divided into smaller intervals on which then the problem can be solved in digestible ways, to put it simply. So that would be the contribution that Professor Khumalo and his collaborators have made in this area. This is significant because following their the papers that they've published in this area, some other researchers got inspirations and later developed their own methods, building up on what has been contributed by Professor Khumalo's team. So in closing, I would say this is one of the significant impacts of his research in terms of contributing to the body of knowledge and literature in this area. So introducing methods that are accurate and giving more reliable results that would then make sense in terms of interpreting the results for policymakers.
Thank you, Professor Khumalo, for a lecture that's so educational, very informative, that acknowledges the extent of your scholarship, that acknowledges its societal significance. Thanks to you for having made us listen to such a wonderful ways of finding solutions, mathematical solutions that are computational, to bring about the change, not just only for the sake of scholarship, but also for the sake of solving a number of problems that needs to be solved using all the irritations that you actually have made too in terms of the recommendations. We appreciate you for that. I also appreciate Prof. Motsa, who actually has given up his work at Eswatini University to be a respondent of this lecture. Thank you for an engaging response that's calling us to much more action, to much more research and scholarship for the benefit of the African continent, and of course, by extension, for future work that Prof. Khumalo will need to take into account. Thank you, ladies and gentlemen, boys and girls, family, alumni, founders, industry partners, departmental, in the government sector, colleagues who've been able to grace this lecture this evening. Thank you for your support and for supporting in particular the work of Prof. Khumalo. I express a gratitude singling out colleagues who've worked hard behind the scenes. The fact that you're able to hear me right now, it's because of colleagues of the Video and Media Multilingual Center who've made it a point that we are audible, you can see me well, and who have ensured that our facilities to get this lecture done are in order. Indeed, before we have such lectures, we will not have had the lectures successful without a lot of work that's done by colleagues in the corporate affairs who engage us to ensure that these lectures become a success. The Department of Institutional Advancement, the IT colleagues, facilities colleagues, etc. So continue to congratulate Prof. Melusi Khumalo and put on expectations on him of what do we expect of him now that he's a full professor. He shouldn't just walk the path good without delivering some of the expectations. Good evening. Thank you.